The next talk is by Sreejata Kishor Bhattacharya. He's a graduate student here working with Arkadev. Uh, he'll be talking about exponential lower bounds for ResLin proofs for near quadratic depth.
Hello. So this talk will be on proof complexity, and this is joint work with Arkadev Chattopadhyay. So this talk will be on proof complexity, and the central task of proof complexity is the following. You're given an unsatisfiable CNF, and you have to produce a certificate that this CNF is unsatisfiable. And this certificate should be efficiently verifiable. That means a computationally bounded person should be able to look at the certificate and be convinced that the CNF has no solutions. So I'll start by describing the most basic and well-studied proof system. This is called resolution. And this is how resolution works. Suppose you have two clauses in your CNF, A or X and B or not X. Note that these two together imply A or B. So you're given the CNF, which is the set of clauses C1 to Cm. And from this set of clauses, you try to find two clauses which are of this form, and you derive a new clause. Yeah, so not short proofs don't always exist. I'm coming to that. If a short proof always existed, then NP equals to CoNP. But short proofs don't always exist. This is in the next slide. So your initial set of clauses is C1 to Cm as given in the CNF. And you try to find two clauses which are of this form. And sorry, where's the laser pointer? Yeah. You try to find two clauses which are of this form and you derive a new clause. And you keep deriving new clauses until you reach the empty clause. Now the empty clause is always false. So a derivation of the empty clause is a certificate that the CNF is unsatisfiable. And it's known that every unsatisfiable CNF has a resolution refutation. Now, can we expect that every unsatisfiable CNF has a small resolution refutation? Small as in less than equals to polynomial in n. And the answer is no, because that would mean NP equals to CoNP, and we don't expect this to be true. So the natural question now is, can we construct an explicit small CNF which requires resolution refutations of exponential length, or at least super-polynomial length? So this was first done by Haken, and he showed that the pigeonhole contradiction in appropriate encoding requires exponentially large resolution refutations. Now, what about other proof systems? There are proof systems that are stronger than resolution, and I will describe some of them. Now, without going into too much details, for every circuit class C, there is a proof system called C Frege, where every proof line is a circuit which is a member of C. So in resolution, every proof line, as in every new thing that you derive, is a clause. So resolution would be clause Frege. Similarly, for AC0, we have the corresponding proof system AC0 Frege, where every proof line is a constant depth circuit. And similarly, we have AC02 Frege. For NC1, that's formulas, we have NC1 Frege, which is also known as just Frege. And for P by poly, we have P by poly Frege, which is also known as extended Frege. Yeah, so every proof line is a constant depth circuit, and there is a set of derivation rules. As in, from this circuit, the derivation rule will say a circuit of this form and the circuit of that form will imply a circuit of this form. There will be a fixed set of such derivation rules, which you can substitute circuits in there. And it does not matter what this fixed set of rules says, as long as they are complete, any two such systems will be polynomially equivalent. So P by poly Frege is called extended Frege, and formula Frege is called just Frege. And that's just a notation. I don't know why we use this. Yeah. So this is the next slide. So this is Cook's program. We hope to prove, like maybe in a million years, that we'll prove NP not equals to CoNP by proving lower bounds against increasingly stronger proof systems. So ultimately, we'll have to reach something that's above extended Frege. And there are also these other proof systems like cutting planes, SOS, polynomial calculus. I'm not going into those. So here the frontier is that we have lower bounds for AC0 Frege, but we do not have lower bounds for AC02 Frege. So as soon as you add the power of parity inferences to AC0 Frege, we don't have lower bounds anymore. And to understand the situation better, Itsykson and Sokolov suggested the following. We know that as soon as we add the power of parity inferences to AC0 Frege, we don't have lower bounds anymore. So instead, let's try to augment resolution with the power of parity inferences. And let's try to prove lower bounds against this proof system. And this gave rise to the proof system that's known as ResLin, where you essentially augment resolution with parity inferences. I'll describe this in the next slide. And proving lower bounds against ResLin is a major open problem in proof complexity. Then this is the frontier now. We have lower bounds for resolution and AC0 Frege, but we do not have lower bounds for AC02 Frege. And we also do not have lower bounds for resolution augmented with mod 2 inferences. And this is like putting ResLin below this frontier is a major challenge. And now I'll define what this ResLin proof system is. Yeah. Yeah. But they don't translate to. So the way the AC0 Frege lower bounds work is that you note that random, if you have a refutation of a CNF and you hit it with a restriction, the restricted CNF also has a small refutation. We have a Hastad switching lemma for AC0 that gives AC0 lower bounds. And that essentially gives rise to the AC0 Frege lower bounds. And this thing we have Rasborov-Smolensky for AC02. So why doesn't that give rise to AC02 Frege lower bounds? So the way this proof work is that you have, let's say you have a AC0 Frege refutation of a CNF and you hit it with a random restriction. Now the restricted CNF will have a AC0 Frege refutation where each circuit is hit with the corresponding restriction. Now we know AC0 circuits get simplified when they get hit by random restrictions, but we do not know if AC02 circuits get simplified if they are hit by a random restriction. Yeah, so the random restrictions don't simplify.
Okay. And once again, I have another question with respect to the frontier that you drew. The next slide had the frontier. No, the next slide had the frontier. So AC0 Frege, supposedly it's gone. We have understood. But even there, do we know against random?
So there's a paper on ECCC last week which claims this, but the proof is very shady and it does not even give a proof.
No, so AC0 Frege is put under the frontier that we understand it. But typically when we understand it, we also say that a random unsatisfiable formula, we can show lower bounds for it. And that is the case for resolution, at least. That's
Okay, so there was a paper on ECCC last week which claimed this, but
okay.
The proof is very shady and nobody is believing
it. Okay, thanks.
Yeah, so I will define ResLin now. So here, every proof line is a linear clause. Now, what's a linear clause? Note that a normal clause is just a conjunction over bit variables. You say either x1 equals to b1 or x2 equals to b2 or so on. Here, every proof line is a conjunction of linear forms over f2. Here, you say either the inner product of a1 comma x equals to b1. This is all happening over f2. Or the inner product of a2 comma x equals to b2 or so on. These are your proof lines. And these are the inference rules. The first inference rule is weakening. So let's say you have two linear clauses C1 and C2, and C1 semantically implies C2. then you can derive C2 from C1. And note that checking if C1 semantically implies C2 is easy because it's equivalent to negation of C2 contained in negation of C1. And negation of C2, negation of C1 are both affine spaces. So you're checking if one affine space is contained in another affine space, which is easy to check. And the second inference rule is resolution. So let's say you have two equations, two clauses. The first clause is A, or some inner product of X with V is B. And the other clause is B, or inner product of X with V is 1 minus B. Then note that these two clauses semantically imply A or B. So you can derive A or B from these two clauses. And this is one reason ResLin is more powerful than resolution is you can do many cool things in ResLin. One example is this. Let's say you have a linear clause. Note that its negation is an affine space. So you can write this affine space in any other basis. And that negation will be another linear clause, but semantically they're the same linear clause. So you'll be able to derive this other linear clause from the original linear clause using weakening, because you know semantically they are equivalent. And now we have a very different form of the same linear clause. So you can use this new form to resolve against other linear clauses. And this can give you more power. And it's indeed known that ResLin is exponentially more powerful than resolution. One example is the Tseitin contradiction over expander graphs. I'll come to this CNF later. So here, any ResLin always has a constant, as a small refutation. But if the graph has some nice properties, no small resolution proof exists. And in the last symposium, I presented our work on separation between unrestricted ResLin and regular ResLin. Since then, there has been a line of work focusing on lower bounds on depth-restricted ResLin. And so what's the depth of a ResLin refutation? Note that every refutation can be seen as a DAG. If you derive one clause from two other clauses, you add an edge from those two clauses to the derived clause. And this naturally gives you a DAG, where at the root there is the empty clause, and at the leaves there are the axioms. And the depth of the clause is simply the length of the longest path from the root to an axiom in the underlying DAG. Now, Arkadev and Itsykson in 2024 exhibited a CNF with small size with on n variables, such that any ResLin refutation of depth order n by n log n requires exponential size. Now, if we can replace this n log n to something super polynomial in n, we have lower bounds for unrestricted ResLin. And this is what we would like to do. So the current program is improving this depth. And in 2025, Efremenko and Itsykson removed one log factor. They exhibited a CNF, actually the same CNF, such that any ResLin refutation of depth n log n requires exponential size. For some reason, their proofs seem to get stuck at this n log n barrier, and they posed the following open problem. Exhibit a CNF with at most polynomially many clauses, such that any ResLin refutation of depth at most n power 1 plus epsilon requires super polynomial size, where epsilon is some constant we are allowed to choose. And in this work, we exhibit such a lower bound. We construct a CNF such that every ResLin refutation of depth at most n power 2 minus delta requires size exponential in omega tilde of n power delta. So in particular, we get lower bounds for depth 1.999999, which is more than 1. And in the next few slides, I'll describe this CNF, and then if time permits, I will provide a proof sketch. Yeah.
Is the statement false or does the proof get stuck?
Proof gets stuck. So this is
we
the
still
next.
expect the
This is the next frontier now. Improve it to more than n squared.
Okay, thanks.
They're actually in the.
No, it's believed that the CNF we get does not have any small ResLin refutation at all. It's believed, it's not proven, but we can prove it. Yeah. So I will describe the CNF in the next few slides, and if time permits, I will provide a proof sketch. So we'll construct the CNF in the following manner. First, we'll take a base CNF psi, and then we'll lift it by an appropriate gadget G. And the final CNF will be psi lifted with G. So before describing what psi is, I will describe how you lift a CNF. Yeah, we define lifted CNFs in the next slide. So let's say your base formula phi is a CNF formula on the set of variables x1 to xn. And G is a gadget on B bits. Now the composed CNF phi is the following CNF formula. In the variable set, for every variable in the base CNF, in the base formula, you add B more variables. So the set of variables is y I comma j, where I is a variable in the original CNF and j is between 1 and b. And semantically, you want to say the following. The original CNF, the lifted CNF evaluated on y is equivalent to the base CNF lifted on g of y1, g of y2, dot 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 g of yn. So you want to say whether lifting the CNF, you just apply g to the lifted CNF and you get the original CNF. And there's a way to enforce this by looking at the clauses of the base CNF and brute forcing over the truth table of G. So I will not provide the explicit construction here, but it's not hard to do. It's easy to see. And you can show that if the maximum width of a clause of the base CNF is W, then the number of clauses in the lifted CNF is initial number of clauses times 2 power BW. So y1 is y1, 1, y1, 2, dot, 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 y1, b, and so on. And the way you do is you look at every clause of the base CNF and you lift that clause. By lifting that clause, you do some brute force over the truth table of G and see which assignments are not allowed, and you write them down in a CNF form. So in particular, if the base CNF is constant width and the gadget size is order log n, then the lifted CNF has polynomially many clauses, which is what we want. And now we'll describe some properties of the gadget that we need. The property of the gadget that we need is that all its Fourier coefficients are exponentially small. So first we set the gadget size to be around 1000 log n. This can probably be reduced to 2, but we don't care. And every Fourier coefficient of the gadget has magnitude at most 1 by 2 power b by 5. And one concrete instantiation of such a gadget is the inner product function. And okay, I will define now I will define the base formula. So the base formula is the Tseitin contradiction over a constant degree expander graph. Now, what's the Tseitin contradiction? In words, the contradiction is the following. We are given a graph with an odd number of vertices. And this is the contradiction that we will express in CNF form. There exists a subgraph of this graph such that every vertex has even degree. Now, we know such a subgraph cannot exist because if you add up all these equations, you get 0 equals 1 mod 2. So this is a contradiction. So formally speaking, the set of variables for every edge in the base graph, there is a variable z u comma v. And if z of u comma v equals to 0, it means this edge is not in your subgraph. And if z u comma v equals to 1, it means this edge is in your subgraph. And for every vertex v, we express the constraint that the sum of all its neighbors is 1 mod 2. And if the degree is d, to express this in CNF form, we need 2 power d clauses. And we'll take d to be constant, so 2 power d will also be a constant. No, but for the lower bound, we need an expander. And yeah, this CNF is unsatisfiable because if you add up all these equations, you get 0 equals 1 mod 2. So we take this base CNF, where the graph has sufficiently good expansion properties, and we lift it with the inner product gadget, still any gadget with small Fourier coefficients. And the final formula is this Tseitin contradiction lifted with the gadget G. And now I'll show a very brief proof sketch. And before that, I'll define some terms. I'll just define one thing. I'll define what's a lifted distribution. So let's say you have a distribution mu on the base space. And I define its lift, G inverse of mu, to be the output of the following sampling procedure. First, you sample Z according to mu. Z is an element of 0, 1 power n. And you sample X uniformly at random from one of its pre-images and return X. And any such distribution is called a lifted distribution. And I'm now going to provide a very brief proof sketch of our result. Sorry, how much time do I have left? Okay. And our proof follows by modifying the approach of Efremenko and Itsykson. At one point in their proof, they were sampling points according to the uniform distribution on a set, and they were applying a bottleneck counting technique. Our main observation is that instead of sampling from the uniform distribution, we can sample from the any lifted distribution as long as the gadget has all Fourier coefficients of small enough magnitude. And allowing ourselves to sample from any lifted distribution offers us a lot of flexibility to improve the proof parameters. And to get an improved lower bound, we have to choose the distribution wisely. And this reduces to solving a combinatorial problem on the lifted space. And I cannot describe all of this in this time, so I'll just describe a toy version of this in the unlifted world. And I think I'll end my talk there. I'll just describe this toy version, which I think is pretty nice and involves some nice ideas. So let's say we have this Tseitin contradiction over an expanding graph where the number of vertices is odd. Now, our job is to construct a non-empty set of partial assignments to the edges with the following properties. Property 1, no falsification. No partial assignment in this set falsifies any clause of the Tseitin contradiction. Property 2, downward closure. If you take a partial assignment in P and you unfix some of the variables, the resulting partial assignment also is in P. And here is the most interesting property, hardness against decision trees. What this means is the following. Let rho be any partial assignment in P, which fixes at most n by 1000 many variables. Then there exists a distribution mu on the unfixed variables such that the following holds. Let T be any decision tree with depth at most n by 1000. So sample input according to mu. Note that this input is consistent with rho, and run this decision tree on this input set. And you end up at a leaf. That leaf reveals something about the input set. So this leaf this tree gets in some partial information. It sees a partial assignment. We want that with probability 1 by 3, the partial assignment seen by the tree in the end also lies in P. So if you start from a partial assignment in P which does not fix too many variables, there's a distribution on the unfixed variables such that if you sample according to that distribution and query in a few positions, with high probability you still end up at P. And this is the unlifted version of the problem that we have to solve. And I think I've probably run out of time by now, so I'll just end here. So thank you.
Any question?
Hi. So there's a question of proving lower bounds for something, and then there are two sort of moderately related questions. One is to understand the construction of pseudo-random generators for whatever circuits you have proven lower bounds for, and then there's a question of proving proof complexity lower bound. When we talk about these questions in the algebraic setting, we sort of have a sense of what strengthenings of the lower bound proof do you need to get pseudo-randomness? What strengthening do you need to understand proof complexity, lower bounds? And then we also understand some correspondence between them. The kind of strengthening we need for PIT is often somewhat related to the kind of strengthening we need in for proving lower bounds. Does something like this also happen in the Boolean setting? For instance, we don't know pseudo-random generators for AC0 parity circuits also.
Yeah.
Is that question somehow related to the question of proving proof complexity lower bounds for AC0 parity?
Yeah, I'm not sure. I imagine the barrier is that we don't have like AC02 circuits don't simplify under restrictions. That's why the AC0 Frege. Yeah.
Random. Yeah, so
Yeah, but my question was related to that. Like usually in like Boolean or algebraic complexity, if you have some measure that you can show that you can use to show a lower bound, your first thing course of action is to show that a random polynomial is hard. And why doesn't that approach work in the in the Boolean proof complexity world? Like,
So okay, we know random CNFs are hard for resolution, but it's controversial. I mean, we don't know if random CNFs work for AC0.
Yeah.
As in, there's a paper in ECCC just last week and yeah, but yeah.
I think we can move some
So I think one more reason is that, in any, if you take a random CNF, any input falsifies a constant number of clauses. So the search problem is actually pretty easy for random CNFs.